Alright, so welcome everyone to this new video where we discuss things on mathematics and physics on the board. Now, today what we are going to do is kind of continue one of the things we've done on exterior algebra before, so that was to provide a sort of geometric intuition of exterior algebra, and we are going to come back to this actually geometric interpretation a bit later. Um, what I would like to do is actually here use some of the properties we've seen of exterior calculus, and in particular of the so-called wedge product, to introduce a notion called exterior calculus. So that's a kind of calculus which is grounded, if you will, in exterior algebra. So let's see how that works. It's fairly simple. Essentially, what you do is to define it. So you want to define the concept of exterior derivative, right? That's what calculus is about. So you want to define the concept of exterior derivative, and traditionally the way it's actually called is simply d. Because the exterior derivative is simply denoted d and nothing else. So what you do here is that, usually to define it at least, is that you start by defining it for what is called, for a scalar field, okay? And so let's say this scalar field is f of, and let's say that for the sake of it, this is going to be x, y, and I'm going to focus to two variables here. But obviously, it could be z, whatever number of variables you want in there. I just want to illustrate it in the case of two here. So let's say you've got a scalar field. Then the way you define the way, but just to say, by the way, that this is sometimes called a zero form. And that's going to be useful if you do differential geometry and so on. Then usually the entities themselves, you're going to call them differential forms, and then you're going to work with them as well. It's not particularly necessary at that stage here. So scalar field f of x, y, and you define df basically the way you would define a traditional total differential. So that's simply df dx plus df dy dy. Nothing more. Okay, there is nothing special really about this. But then what we are going to see is what happens when we try to have something else. So now imagine that instead of a scalar field, I've got what is called a one form, and in particular a one exterior form. And so in which case usually it's called omega. And I've got omega, which is equal to, yes, so we've got omega, which is equal to, let's say, g dx. So we've got omega, which is equal to g dx, and then plus h dy. Okay? So here I'm authorizing myself to actually imagine that I can have basically an object that is written like this. Okay, and you can view that as basically, as a differential. So you say, oh, the variation, well, no, that there is a quantity that is equal to g dx plus h dy. Okay, that could be something you get when you calculate the circulation, for example, of a field along a curve or something like this. Okay, so g dx plus h dy. Okay, now you actually define the derivative. You can define the derivative of that stuff in the following way. So the exterior derivative of omega is equal, by definition, so that was the definition here, by the way, by definition, it's equal to dg and then wedge dx plus dh wedge dy. Okay, where here dg is basically, g is considered as being a scalar field, so I can use this definition, and dh again is used as a scalar field here. So let's see what that gives. So if I actually do dy, so I've got d omega is equal to, so dg wedge dx, so dg is going to be dg dx plus dg dy dy, and that's wedge dx, and then we've got plus dg dx dh, sorry, dh dx plus dh dy dy, and then wedge dy. Okay, now please remember that we've seen before that dx wedge dx is equal to dy wedge dy is equal to 0, and that's due to the property of the exterior product, the wedge product. Okay, and so what we are going to get is that d omega is equal to dg dy, and then dy wedge dx, and then plus dh dx, and then dx dy. Okay, now the next property that you need to remember with the exterior product is that dy dx is equal to minus dx dy. So therefore what we get is basically that d omega is equal to dh dx minus dg dy, and then we've got dx wedge dy. I think this is important enough that I should highlight it, because this one is the outcome, if you will, of a sort of derivation. And basically that's it. Now, of course, you can extend this. So, by the same token, if you have, a form omega, in fact, I invite you to actually look at it. So let's imagine that you've got a form omega, which is equal to the following. So you're going to have a function g. Well, actually, in that case, that would be simply g dx wedge dy. Okay, and you can try to see what happens in that case. What you will see is that you're going to get 0, in fact, in that particular case. And the reason why you're going to get 0 is because if you've got omega, which is g dx dy, then any partial derivative you're going to get is going to be in front of a dx or a dy, but you already have a dx and a dy there. So by applying that rule, you're going to get 0. So if you try to get this one here, you're going to automatically get d omega is equal to 0. So if you will, that's a sort of theorem. Okay, that's a sort of theorem. But there is a more important theorem that comes about, which is that basically if h is corresponding to, so that's if you will, that's a sort of theorem. Okay, and the theorem is the following: is that if h is equal to df over dy, and g is equal to some df over dx. So essentially, they are each actually partial derivatives with respect to y and x respectively of the same function. Then we find that we are going to get d omega is equal to the second derivative of f and then x, y, minus the second derivative of f, and then y, x, and then dx, dy. Okay? And so what that means in our case is that this thing is equal to actually the second exterior derivative of f. And what we see is that it's automatically 0 because these terms are the same. So the second derivative, the second exterior derivative is always 0. Okay, so for any omega, so for any differential form that can take that can be a 0 form, a 1 form, so expressed in terms of simply dx, dx, etc., or even a sum of basically 2 forms like this, or wedge product like this, it's always going to give you 0 if you apply it twice. Okay, so that's really a very important kind of theorem, is that d of d omega is equal to 0. Whatever omega is, whatever kind of the dimension of the space you're looking at, and so on. Okay. So I think before I actually stop, I'm going to very quickly tell some nomenclature, if you will, that maybe some of you can connect to some things you've seen in mathematics or in thermodynamics. Okay, so essentially what we have is that we say that a form, so usually it's called a differential form. So anything that is expressed in terms of sums of like this, multiple wedge products, that's fine. So this is going to be called a differential form. So differential form omega is called, and here that's closed if you've got d omega that is equal to 0. Okay, and exact if there exists f such that omega equals df. Okay, and so a corollary from it is that all exact forms are closed. Okay, but the opposite is not the case. Okay, so it's not the case that all closed forms are exact. And usually these kind of basically the distinctions are made, for example, in thermodynamics. So typical things for the omega we had before, for example, would be the work. If you try to calculate the work that is done during a particular thermodynamic process, that's an example of a one-dimensional differential form, and so on and so forth. Okay, so all exact forms are closed, but not necessarily the other way around. All right, so that's how you would use exterior derivative. And what we are going to do next time is actually see how this can be used to generalize basically the notion of integration.